Hello, welcome to General Chemistry 1. My name is Daniel, and today we're going to take our first introduction at the periodic table. The periodic table is probably something you know as like the basis of chemistry, and that's true. The periodic table is something that allows us to organize all the different elements that occur in chemistry, and organize them in a systemic way that we'll look at in this video. So, here's our periodic table. So, there's two kinds of organization we can see in the periodic table. First off, the columns here are what are called groups. Across the periodic table, the rows are what's called periods. So we can just count these. There's period 1, period 2, 3, 4, so on and so forth. Then there's group 1, group 2, group 3, skip over here, go group 13, 14, 15, 16, 17, and lastly on that last column, 18. Now another kind of organization that happens to occur in the periodic table is the organization based on three different categories: metals, semi-metals, and non-metals. So our metals are all on the left side of the periodic table. All of this area. All of these are metals. We'll get into the specifics of each group later in the video. On this staircase right here, let me do it in green. Anything that's touching this staircase, so that's boron, silicon, arsenic, up to aluminum, is what's known as a semi-metal. And then everything else on the right side, I'll do that in yellow, is what's known as our non-metals. So these three different types of materials all have different properties, which we'll get into now. So first we'll look at metals. Metals are good conductors of heat and electricity. That's why we use copper wire in our circuits. They're also what's known as malleable. Malleability is just the ability of something to deform without breaking when we add a compressive force to it. So, for example, a coin or foil. You can flatten out the metal by compressing it and it won't break. That's one of the big properties of metal, and that's why all of our coins are metallic. Metals are also what's known as ductile. Ductility is just the ability of a material to form a wire. So you would take, a piece of metal and stretch it out, and it wouldn't break, and it would form a wire. Copper is in fact one of the most ductile metals, and that's why also another reason why we make wires out of it. Related to ductility is tensile strength. Tensile strength is just it's the strength of material to withstand fracturing when you tear it, or when you pull it apart, I should say. So if I have this metal sheet again and I pull it out, the amount of force that I can apply without it fracturing in the middle is related to its tensile strength. And then lastly, metals also have that characteristic luster. They're pretty shiny, usually gray, shiny-ish, something like that. I'm sure you've seen metals, anything like steel or iron, things like that. So let me get into our metalloids. So our metalloids share properties that are in between metals and nonmetals. So they're more brittle than metals, which are very strong, but less brittle than our nonmetals. They're also what's called semiconductors of electricity. That's why silicon is one of the biggest semiconductors used in electronics, all those things. Some metalloids possess a metallic luster, others don't. But the important thing to take away from this is that metalloids have properties that are somewhere in between metals and nonmetals. So then lastly, we go to nonmetals. So nonmetals are poor conductors of heat and electricity. They're generally brittle. And in fact, most of them are gaseous at room temperature. A lot of the ones in the upper right-hand corner of the periodic table all occur as gases. One important exception here, it comes with carbon. So elemental carbon comes in two forms. On the left here, we have graphite, which is used in your pencils. It's very soft, very non-conductive. On the other hand, if you align the carbon atoms in a certain different way in this pyramid structure here on the right, you get diamond. Now, as you know, diamond is very shiny, it's very strong, in fact, one of the hardest materials known to man. So that's just a difference of the way the carbon atoms occur. Graphite has these hexagonal sheets, whereas diamond has this kind of pyramid-like structure. So diamond's one of the big exceptions for the nonmetals. But for the most part, they're all going to follow those properties we just went over. So now we're going to get into atomic notation, how to read things from the periodic table, how to ascertain information from it. So in the periodic table, your general periodic table will look like this. You have this number in the top left, you have this number on the bottom, and these are what's known as, this is the atomic number, this is the mass number. So the atomic number is just the number of protons that are in the atom. The mass number is the number of protons plus the number of neutrons. As we saw in the last video, protons and neutrons are what make up the mass of atoms. And so the atomic mass is just the mass of each carbon atom from its protons and neutrons. However, when we write it out as a isotope or a separate thing, we're switching around the numbers. So the mass number would be on top when we're writing it in a reaction. The atomic number would be on the bottom. And then lastly, if we had a charge, this is a neutral molecule, but let's say we had a charge up here, like +1, -1, whatever. Your charge on your molecule is just equal to the number of protons minus the number of electrons. So if we have more electrons than protons, we have a negative charge. If we have less electrons than protons, we have a positive charge. And if the number of electrons equals protons, we have no charge, an uncharged species. Okay? So using that information, we can do things like use given information to ascertain other things that aren't given. For example, here in this first one, for helium, we know it's the element helium, we know its charge and number of protons and neutrons, but we don't know anything else. But we can determine those things from what we're given. So, as we just said, atomic number is just equal to the number of protons. So that's just going to be 2. The atomic mass is the sum of protons and neutrons, so that's just 2 plus 2, which is 4. Number of electrons, since this charge here is 0, is going to equal protons, so that's just 2 as well. So we'd write out helium like this. Helium, no charge, 4 is the atomic mass number, 2 is the atomic number. For the other examples, let's look at carbon. So carbon, we're given the atomic number, the mass number, and the charge. We're not given anything about the particles inside it. Once again, the atomic number is just number of protons, so that's just going to be 6. The number of neutrons is just, we can just find that doing the mass minus the number of protons. So that's just going to be 6 again. And then number of electrons, since we have a 0 charge once again, is going to be equal to the number of protons. So that's going to be 6. Now in this next one, we don't know the element. But using the periodic table, we can figure out which one it is. So if you look at your periodic table, you'll see that element number 26 is iron. We also know that there's 26 protons and 30 neutrons. So 26 plus 30 is 56 for our atomic mass number. Now in this one, we have a positive 2 charge. So this is an ion. Since we have a positive 2 charge, there's 2 less electrons than protons. So that's going to be 24 electrons. Because for that one, if we do number of protons minus number of electrons, we have 26 minus x equals 2. Then x equals